Assalamualaikum warahmatullahi taala wabarakatuh. Very good day. I greet to all of the listeners of this video. My name is Syamsul Imran Zaini from University of Malaysia Pahang. So today I would like to present about ground improvement of soft kaolin clay reinforced face and encapsulated bottom edge column. From what we know, soft clay soil is one of the complex soils encompassing parts of the ground, including numerous lowland and coastal areas where many metropolitan and industrial areas are found and regularly confronted in civil engineering projects. So in the study, the ground improvement technique by means of concrete or granular inclusions in either partially saturated or fully saturated, which jointly create a reinforced ground, has been extensively utilized to boost the strength, minimize the settlement, and also regulate the movement of the ground. So the use of bottom edge in ground improvement as a green substitute to the soft clay soil is gaining considerable momentum, and it is vital that there exists true comprehensions of the characteristic of bottom edge and its influence on the characteristic of problematic soils. So to achieve the objective of the study, we designed the experiment by using the singular encapsulated bottom edge column and also the group of encapsulated bottom edge column, as you can see from the figure. And all of the laboratory tests are conducted in accordance to the British standard of the ASTM. So for the experiment setup, we use uh, three types of laboratory tests, which we want to determine the physical properties, we want to determine the mechanical properties, and also we want to determine the shear strengths. As you can see from the figure, it can be concluded that the highest improvement of shear strength recorded for single encapsulated column was 77%, denoted with the green box, with a column diameter and column height of 10 mm and 80 mm respectively, while the lowest shear strength improvement recorded for the single encapsulated bottom edge column was 54.23%, denoted with the blue box, with 10 mm and 100 mm of column diameter and column height respectively. At 10 mm column diameter and at a column height of 80 mm, the single encapsulated recorded the highest shear strength improvement for all the samples tested to improve the shear strength of the soft kaolin clay. As you can see from the figure, for the first figure, it shows that the effects of area replacement ratio to the shear strength improvement of kaolin soft kaolin clay sample. So as you can see, it can be concluded the shear strength for the group encapsulated bottom edge column yielded to a smaller improvement of shear strength due to the high value of area replacement ratio of column, which affect the surrounding column area. As the vertical load was distributed inside the column, the bulging occurred in the column as the remaining width of the soil sample was too thin to hold the columns. The initial shear strength of the soil itself decreased when large portion of the soil was drilled from the specimen before the bottom edge were installed. The second figure shows that the effect of height penetration ratio to the shear strength of the soft kaolin clay sample. Okay, as you can see from the figure, it can be concluded that the shear strength of kaolin clay will increase as the length of penetration increases. Although there is an increment in the shear strength, however, the improvement of the shear strength does not merely depend on the HR or the high penetration ratio of single and group encapsulated bottom edge columns only. The portions of soft clay was substituted with a stiffer material like bottom edge, and the columns was encased with a textile that help in drainage. Thus, the significant increment in percentage of shear strength can be considered substantial as the penetration of single and group encapsulated bottom edge columns was increased. The smaller diameter of the encased bottom edge column shows a better performance compared to the bottom edge column with bigger diameter. This is because of the mobilizations of the higher confining stresses in the larger bottom edge columns, which is coherent to the previous result obtained by Nagy 2013. Next, for this figure, it shows that the effect of height diameter of column ratio to the shear strength improvement of soft kaolin clay sample. So as you can see, or as what can be concluded from this figure, using bottom edge columns proves that the HDR do influence the degree of improvement in soft kaolin clay, as reported by Hassan 2013. There was a decrement of shear strength at fully penetrating column with a bigger diameter due to the large fractions of soil replaced by bottom edge particles. Thus, it affected the natural state of the soil and causes the reduction in the shear strength of the samples. The shear strength of kaolin clay will increase as the HDR value increases until the peak improvement of shear strength is reached at 8 HDR value. Then the shear strength will decreases due to the weak structure and the weak bonding particles of the sample. Although there is an increment in the shear strength, however, the improvement of the shear strength does not merely depend on the HDR value only of the single and group encapsulated bottom edge columns only. So there are several factors that affect the value of the shear strength. Next, the figure shows the effects of volume replacement ratio to the shear strength improvement of the soft kaolin clay soil sample. So as what can be summarized from the figure, the highest VR value recorded was at 30.80 for G16100 samples, with the lowest VR value recorded at 2.40 for S1060 sample. The optimal improvement of shear strength recorded was at a VR value of 3.20. Hence, the data proves that the higher value of PR do not contribute to the higher improvement of shear strength. However, all the data do effect the changes in the shear strength improvement when compared to the control sample. Based on the previous work by Hassan, there will be huge possibility for the soil to collapse since there was no confining pressures imposed on the soil samples during the test. From this table, what can be said is that the friction angle for a given soil is the angle on the Morse circle of the shear stress and normal effective stresses at which shear failure occurs. Higher shear stress and normal effective stress will result to higher friction angle, as verified by Frika et al. 2015. The particle size of the column material had a tremendous effect on the behavior of reinforced clayey soil, including the rigidity, friction angle, and the characteristic of the shear strength. Hence, in this study, the bottom edge column installation at various dimensions and arrangement lead to higher stress and effective shear stress. The data validated that there is an effect to the friction angle when the shear stress and the effective normal stress increase, as what can be seen from the table. As for the conclusions, it can be said that kaolin clay can be categorized as low plasticity. The shear strength of the soft clay was significantly enhanced by installing the encapsulated bottom edge columns. The AR and HP have a great influence in improving the shear strength of reconstituted soft clay reinforced with encapsulated bottom edge columns. The highest improvement of shear strength of 10 mm and 60 mm for both single and group encapsulated bottom edge columns was at 0.8 of HP, which is we call it as a critical column length. The study, therefore, concludes that the utilizations of encapsulated bottom edge columns firmly influence the engineering properties of the kaolin clay as an effectively ground improvement. It is therefore recommended that single and group encapsulated bottom edge columns with a 10 mm column diameter and 80 mm column height should be used by practitioners to improve the kaolin clay for construction applications, as the improvement to the ground can be reached up to 77%. Thank you.